Come to third class of biomolecules. First, I will like to give you a recap of last class. In last class, we discussed about structure of aldoses, particularly configuration of aldoses, and there we talked about D-aldoses particularly, and then we also discussed about the configuration of ketoses, and there we discussed different type of D-ketoses, and finally we were talking about the structure of structural formula of monosaccharides. While talking structural formula of monosaccharides, we discussed the different kind of representations, particularly Fischer projection formula, and there we learned that how sugar molecule can be represented in a two-dimensional format. Fischer projection formula is also known as cross formulation. Why it is known as cross formulation? Because of the way of presentation is like we keep the main functional group on the vertical line and hydroxyl group we keep on the carbon chain. I have already given you example of the D-glucose. So, today I will show you some models, and through that we will try to understand in a better way. The meaning of formulas can be seen through the use of molecular model, and here you can see that I have taken here this carbon chain. Carbon chain here stands for like carbon number 1, which has the aldehyde functional group, carbon number 2 which has hydroxyl on the right hand side and hydrogen on the left hand side, then carbon number 3 which has hydroxyl on the left hand side and hydrogen on the right hand side. Similarly, carbon number 4 where hydroxyl is on the right hand side and hydrogen on the left hand side, and carbon number 5 has hydroxyl again on the right hand side of the carbon chain and hydrogen on the left hand side, and finally the last carbon CH2OH is attached. So, if you look over this molecular model, you can see here that how this aldehyde group is projecting away from us, whereas hydroxyl and hydrogen are projecting towards us. So, aldehyde group and this CH2OH which is going away from us, and if we leave it freely, then it tries to approach towards the aldehyde group, this CH2OH attached hydroxyl group. So, now again I will like to talk about that if we leave this open chain conformation, it tries to attain a kind of cyclic or spiral structure, and that basically has been observed in the structure of glucose, that it does not remain as a linear form, it attains a cyclic form. All right. So, what are those cyclic forms? We have already discussed about the Fischer projection formula, which is a linear form. The other possibility from the Fischer projection formula that one can attain is cyclic form, and that is also known as Haworth formulas, which is cyclic in nature. So, I will show you, this is the Fischer projection formula which is cross formulation, and there we also learned about that wedge line dashed wedge formula. Now, I am talking about the the cyclic formula, which is you know having a 6-membered ring, and that 6-membered ring having oxygen as a heteroatom and other 5 members of the 6-membered ring are carbon. Now, I will explain it that how this 6-membered ring is forming. I have already mentioned that the linear form, the Fischer projection form, what we have discussed already, it does not remain in reality. So, this is the cyclic form. Cyclic form, again I am taking here the linear form through this chain of carbons, okay, and I am leaving it. If you see that when I leave it freely, then again this aldehyde is approaching towards the hydroxyl of the 5th carbon, and that structural arrangement leads to the cyclic structure of the sugar, basically of the glucose part, particularly in this case. So, what are we doing? We are just putting it in a free form, and that free form gets the cyclic structure. Now, once this hydroxyl approaches the aldehyde of this carbon chain, it reacts with the aldehyde, and as we know that reaction of aldehyde and alcohol leads to the formation of acetal, and that basically the cyclic structure is acetal. In other words, we can say that the glucose which we consider as a linear form, it is not linear, it is a mixture of cyclic as well as the linear form. Here I have drawn from the linear form, I have drawn here the cyclic form. This solid line representation means if we consider the Pyron ring in plane, this the solid line comes towards us, whereas the oxygen containing part is going away from us, and on this ring different substituents are there. So, one possibility, if aldehyde group gets attacked by the hydroxyl, it can lead to the hydroxyl down, and other possibility where the hydroxyl can go up. So, I will draw the other possibility. Again I am putting this solid line just to make you feel that this part of the ring is towards us, then other part is away from us. The rest 2. So, what is happening here? The OH group of C2 is placed on the right side, and that of C3 on the left side, and those of C4 and C5 on the right side. This cyclic form, this cyclic representation basically is known as Haworth formula. Haworth formula, and these two cyclic form where hydroxyl is opposite to the orientation of CH2OH, that is known as alpha D glucopyranose, and where the hydroxyl is on the same side of the CH2OH, then it is called beta D glucopyranose. Now, I will draw the chair conformation of these structures to make you understand in a better way. So, I am drawing here chair conformation. So, in the alpha D glucopyranose, hydroxyl is axial at the first carbon, and in the case of beta D glucopyranose, it is equatorial all right. Now, I am assuming that you have better concept of cyclic structure, that Haworth formula, which I explained you with the help of the model, that how this cyclic structure forms. First, I talked about the Fischer projection formula, where which is also known as cross formulation, where we can see that on the carbon chain, basically hydroxyl and hydrogen are on the both the sides, and if we leave it freely, then hydroxyl of fifth carbon comes closer to the aldehyde group, and it reacts and forms the acetal, and that leads to the formation of cyclic structure, which is acetal in nature, and that acetal can be the alpha form, or alpha cyclic form, or it can be the beta cyclic form. And based on the sugar, particularly we started with the glucose. So, here glucopyranose, alpha D glucopyranose and beta D glucopyranose, these are the two cyclic structures are possible. The cyclic form of the alpha D glucopyranose and the beta D glucopyranose, where the orientation of hydroxyl group is detrimental, that from which class, at the carbon number 1, there only it just varies. If you look over the these two cyclic structure, leaving all other stereocenter or chiral center, only the stereochemistry varies at the carbon number 1. Basically, at one position only in both these forms, stereochemistry is different. Rest of the carbons are having same stereochemistry, and that's why this in carbohydrate chemistry, the diastereomer differing only at the hemiacetal or acetal carbon are called anomers. So, in carbohydrate chemistry, diastereomers differing only at the hemiacetal or acetal carbon are called anomers. And the hemiacetal or acetal carbon atom atoms, carbon atom is called the anomeric carbon atom. Anomeric carbon atom. So, the diastereomers differing only at the hemiacetal or acetal carbon are called anomers, and the hemiacetal or acetal carbon atom is called the anomeric carbon atom. The cyclic structures for the glucose anomers are called Haworth formula, which I have already shown you, and each of these glucose alpha and beta are different at the particularly acetal carbon which forms after the reaction of hydroxyl at the C5 position and the aldehydic group. Now, it is not fixed that this cyclization will lead to the only 6-membered cyclic structure, as we have seen in the case of glucose. It can also lead to the formation of 5-membered ring. So, if the monosaccharide ring is 6-membered after the acetal formation, cyclic acetal formation, then it is known as pyranose. Here I will draw the structure of pyran, a pyran, and if the monosaccharide ring is ring is 5-membered, the compound is designated as furanose. So, if the monosaccharide ring is 5-membered, the compound is designated as furanose. I am talking about the acetal, cyclic acetal formation. So, this is the structure of furan, and that is why the cyclic structure is called furanose. Now, I will on the 2-dimensional representation, I will show you that how the formation of this cyclic structure is taking place. First, I will draw the Fischer projection formula, and then I will show you that what reaction is taking place in reality. I have already shown you the Haworth projection formula, and I have also shown you the alpha and beta, chair structure of these corresponding Haworth projection formula. So, let me write the structure of glucose. So, here I am writing the structure of glucose. As we know that it has 6 carbons and aldehyde in its framework and multiple hydroxyl group, particularly 5 hydroxyl group on the carbon chain. This is the glucose. This is the plane projection formula, and this is the model for this plane projection formula. If you see here, this is the model exactly I have drawn. You can see let me arrange it in a proper way. This way. This is the, you can just pay attention that it's very difficult to keep it in a, let me put it again, trying to, yeah. In this case, you can see that CH2OH, this is the CH2OH and this is aldehyde. Basically, this is the aldehyde group attached to the carbon, and this is the, CH2OH, the last one. This is what I am, dangling, basically CH2OH. This is the CH2OH and this is the aldehyde, and rest of the carbons are, substituted with the hydroxyl and hydrogen. You can see that carbon second is hydroxyl, right side, carbon 2 hydroxyl is left side, carbon 3 hydroxyl is right side, and carbon 4 hydroxyl is right side, and finally the CH2OH group is, going again away from us. If I leave it freely, then as I mentioned that, the carbon at the 5 position is coming closer to the aldehyde group. You can see here 1, 2, 3, 4, 5. 5 position is coming closer to the aldehyde group. So, let me draw the cyclic structure to make you understand in a better way. So, first I am writing the same open chain form, and then to explain it in a 2-dimensional format, I will show you that, how to rotate the bonds to, so this is the carbon which is attached with the aldehyde. It's attached with the aldehyde, carbon number 1, carbon number 2, carbon number 3, carbon number 4, 5 and 6. Now, as I mentioned that what happens that, carbon hydroxyl attached with the carbon number 5 comes closer in this, cyclic presentation. You can see here that this is coming closer. This is the aldehyde. So, 1, 2, 3, 4, 5. I have tilted like this so that it can react, and this is this job I am going to do. So, what I am doing, basically I am rotating along this carbon-carbon bond, this carbon-carbon bond. That is what I am writing over here, that if we rotate along this carbon-carbon bond, carbon 4 and 5, carbon 4 and 5, if I rotate, then hydroxyl will take the position of CH2OH and CH2OH will take the position of hydrogen, and hydrogen will take the position of hydroxyl, all right. And so, let me rewrite with the rotated structure. Rest of the thing will remain same, and only the position of CH2OH and OH will get change. All right. So, after this bond rotation, C4 C5 bond rotation, we get this structure. Now, stage is set for the acetal formation. So, this lone pair will attack on the carbonyl of the aldehyde, and again O minus whatever the alkoxide will form, that will abstract the hydrogen from the alcohol. One thing I will like to mention here that this hydrogen abstraction is not intramolecular. The proton transfer steps occur between separate molecule. The proton transfer step occurs between separate molecules. It is not intramolecular or concerted. It is not intramolecular or concerted. Here it appears, just for the sake of clarity, I have written like that, but generally it happens intermolecular. So, after this cyclic acetal formation, what will be the structure? I am going to write the structure here. First I will draw the pyrrole ring and the anomeric carbon. Here is the anomeric carbon. In one case, the newly formed hydroxyl group is on the same side where the CH2OH, and in other case it is on the opposite side. Let me draw the pyrrole ring here also. So, in this case it is on the opposite side of the CH2OH. I will also like to mention that in both these cyclic structure, what is common is that leaving this anomeric carbon which has the different stereochemistry, all the C2, C3, C4 and C5 have the same chirality, same stereochemistry. So, this is alpha D glucopyranose, alpha D copyranose and beta D glucopyranose. Glucopyranose. Now, let us take a practice problem, how to draw these cyclic structure from the Fischer projection formula or from the cyclic structure or from the chair form of structure, how one can draw the Fischer projection formula just for the practice. So, let us take a problem. Draw the beta pyrrole form beta pyranose form of below given compound. Compound A and a Fischer projection form of compound B. Let me draw these two structure. Let first A So, this is the Fischer projection formula. Again I will draw it in the cyclic format. So, for drawing in the cyclic format I will take first aldehyde. So, let me make the aldehyde and then first carbon attached to it. So, it has hydroxyl group on the right hand side, then the third carbon which has again hydroxyl group on the right hand side, and then fourth carbon where the hydroxyl group is on the left hand side, and the fifth carbon which has hydroxyl group on the right hand side and CH2OH group. Now, this after acetal formation, as it has been mentioned that beta pyranose form. So, I will not consider alpha pyranose, I will directly write the beta pyranose form. In the beta pyranose form, I am putting the all chiral center. So, this is the for the beta pyranose form of the given Fischer projection formula, the structure here. Now, I think you have better understanding. Once you know that Fischer projection formula, then you can translate easily into the Haworth projection formula, the cyclic one for the acetal formation. Now, the second question is the B, draw the Fischer projection formula for a chair form of Fischer projection for cyclic structure. So, I have now you can see on this structure, this is B. Let us open it up so that we can translate it into the Fischer projection formula. So, what I am doing that I am going to open this. This is the carbonyl carbon which reacts with the 5 position hydroxyl group. So, just I will put the CH2OH, this is first, second, third, fourth, 5, 5th, 6th and 7th. So, CH2OH and then again carbonyl which is involved in the, here it is basically involved in the ketal formation, and so the other third carbon is having hydroxyl again on the right hand side, and fourth also having hydroxyl on the right hand side, and then again the fifth hydroxyl is on the left hand side, and finally the sixth one is having on the right hand side and CH2OH. It is very clear that how the carbonyl, this ketose is reacting with the hydroxyl of the carbon chain, and that leads to the this cyclic structure. Now, I will talk about the mutarotation. Mutarotation, as I mentioned that glucose in open chain is very different from the cyclic structure, and in reality it remains as a mixture of the cyclic structure, the acetal structure what just now I discussed with you, because of the cycle formation due to the reaction of aldehyde and hydroxyl of same molecule. Mutarotation we can define with the chiral nature of this sugar molecule, particularly in case of glucose. If we consider open chain form, and consider its ability to rotate plane polarized light, I am assuming that you are well familiar with the concept of chirality, as we know that chiral molecule has ability to rotate plane polarized light. So, this is the open chain form. Open chain form of D-glucose. D-glucose, and this open chain form have given specific rotation plus 52.7, whereas I also showed you the cyclic acetal structure, and cyclic acetal structure I am drawing here in the chair conformation. So, one is having hydroxyl group towards the same side where the CH2OH we have already discussed, that is known as beta D glucopyranose. This is beta D glucopyranose. And the other possibility where it is opposite to the CH2OH. So, this is CH2OH and opposite to that this acetal is known as alpha D glucopyranose. Now, these two crystalline structure can be separated, and it has been observed that alpha D glucopyranose, which has melting point, these two are basically diastereomer, because the if you see the carbon 1 which is having different stereocenter, otherwise all the other 1, 2, 3, 4 chiral centers are having the same stereochemistry, only the anomeric carbon is having the different stereochemistry, and that is why alpha D glucopyranose has melting point 146 degree centigrade and specific rotation close to plus 112, whereas beta D glucopyranose which has melting point 150 degree centigrade and specific rotation is plus 18.7. So, if you leave alpha D glucopyranose as it is, you see here we are having equilibrium among all these structures from the open chain to these two cyclic structure. So, the specific rotation of one form will decrease until unless it reaches to this 52.7, Whereas if you are having pure beta D-glucopyranose, the specific rotation of beta D-glucopyranose will again increase until it reaches to the 52.7. This is the normal D-glucose which I have represented in the open chain form, which gives the 52.7 as a specific rotation. So, a solution of ordinary D-glucose has an initial specific rotation as plus 112. It decreases down until unless it reaches to the plus 52.7, or I can say that a pure solution of beta D-glucopyranose which has specific rotation plus 18.7 increases until unless it reaches to the 52.7. Assuming that the concentration of the open chain is negligible, we can figure out that percentage of cyclic structures available in the solution. So, if we assume that the concentration of open chain is 0, concentration of open chain form is negligible or 0, with the help of a specific rotation by specific rotation we can calculate that in a given solution how much is the alpha D-glucopyranose and how much is the beta D-glucopyranose. So, I am just writing here the these percentages. So, if the open chain is giving 50 plus 52.7, that can be obtained from a mixture of alpha D-glucopyranose where hydroxyl is axial and beta D-glucopyranose where hydroxyl is equatorial. Now, as we know that beta D-glucopyranose has specific rotation of plus 18.7 and the D-glucose where the mixture of both has 52.7. So, how much of the beta D-glucose over there and how much is the alpha D? Here we can easily calculate. If we consider that open chain form is negligible, then 36% of the alpha D glucopyranose and 64% of beta D glucopyranose is available there at equilibrium. At equilibrium. Here I will like to again add one more point that in this case we can see that 64% is the higher quantity. So, it is not true that always beta enomer is the most stable. I will show you another example where alpha enomer is more stable. So, the beta enomer of a pyranose is not always the more stable. As we saw that in a mixture based on the calculation of the specific rotation, we saw that 64% of beta D glucopyranose is there and 36% of alpha D glucopyranose. This should not reflect that beta D glucopyranose is the, or beta D pyranoside is the more stable form. Now I will write here always the more stable. Let me write here a structure where alpha D glucopyranose is more stable. So, here alpha D manopyranose, alpha D manopyranose, and the beta D manopyranose beta D manopyranose. Here it has, based on the specific rotation, it has been observed that it has 69% of the alpha D manopyranose at equilibrium and 31% of beta D manopyranose at equilibrium in a mixture. Now, this anomeric effect is believed to be caused by hyperconjugation. This anomeric effect is believed to be caused by hyperconjugation. I am assuming that you all are familiar with the hyperconjugation. Basically, what happens that an axial oriented orbital associated with the non-bonding electron of the ring oxygen, can overlap with the sigma star orbital of the axial exocyclic CO hemiacetal bond, and that is the reason for the stability of this anomeric carbon, where this overlap between the orbitals of the sigma star orbital of the CO hemiacetal bond with the vacant non-bonding orbital of the ring oxygen leads to the stabilization. Now, I will talk about the glycoside formation. So, let us talk about the glycoside formation. What is glycoside? Glycoside, if you treat D-glucose with acidic methanol, acidified methanol, or you can say that acidic methanol, so D-glucose, I am not indicating that it has alpha D-glucose or beta D-glucose, just simply if you take D-glucose and react it with the acidified methanol, what happens basically, two glucopyranoside forms. Let me draw the structure first. Two glucopyranoside forms. So, this is methyl alpha D glucopyranoside. Again here the orientation at the anomeric carbon and the CH2OH group will define the type of glucopyranoside. Since here it is in opposite side, so it becomes the alpha one. So, methyl alpha D glucopyranoside. Side, and the other possibility where if OCH3 is equatorial, then it becomes methyl beta D glucopyranoside. Now, I will discuss the mechanism that how is it happening. Basically, it is a two-step protocol. What happens that in the presence of acid, hydroxyl group gets protonated and then it leaves and forms the corresponding carbocation, and that carbocation gets reacted with the methanol, and since this is sp2 hybridized, so it has two possibility that it can attack from the either this side or the opposite side, and hence it leads to the these two glucopyranoside alpha D or beta D glucopyranoside. So, let me write here the mechanism of mechanism for the reaction. So, carbohydrate acetals are generally called glycosides, and an acetal of glucose is called glucoside. Similarly, acetal of mannose is called mannoside, and acetal of fructose is called fructoside. So, these are the glycoside formation. Let me talk about the mechanism. How does it happens? So, I will stop here. I will discuss the mechanism in the next class. Thank you very much for the attention. We will meet again with the mechanism of glycoside formation. Thank you.